Now, this is a video for problem session 12, and this was done, as I said here, February 28th, done in Keller Hall 3125, a live lecture. We did that so you could ask questions about the exam, which was given 2 days later. So what I'm doing here is just doing the lecture with the video, and I'm going to copy the notes so that you can have the same material that you would have had for the if we had done it by WebEx and recording. The topic is network sensitivity factors. It requires the linear model, and one of the sensitivity factors that we're going to talk about is called a PTDF, power transfer distribution factor. Now, the idea is, suppose I have a bus over here with a generator on it. I have another bus over here with a load on it, and I'm going to transfer 100 megawatts. I'm going to send it into the bus here, and I'm going to receive it over here. So we call this the send, and this the receive. There's 100. Now, in the middle is hundreds or thousands of transmission lines. And so what we'd like to know, given a transmission line in here with a from and a to bus, how much of that 100 ends up, and we'll do it in the what do you call this? Violet, purple, whatever color. So the question here is how much of the 100 megawatts flows on this line. And if this is the only line that connected those two buses and there's no other loops, then it'll carry all of it. So if there were two buses in the system, even though this is 100. But generally, there's lots of other lines flowing around there, so there's multiple paths. And so the power divides up. And the PTDF gives you a fractional number. And then you multiply the fractional number times this. Okay, that's what that PTDF factor is. The other factor is called an LODF, which stands for line outage distribution factor. And here we have a line which we'll call line L from N to M. And we'll say originally it has a P sub L on it of 0. And over here I have another line from something to something, I don't know, but this is line K, and originally it has P sub K, 0. And line K experiences an outage. Now that we generally call that a forced outage, meaning that it didn't happen because we planned it. And what we'd like to know is if there's a forced outage, if there's an outage on this line, how much of this PK flow ends up over here. And once again, in a system where there's lots of loops, the transmission system, which, by the way, just as an aside, we have loops in transmission systems for reliability. We have multiple paths for reliability so that if one path opens, the power can flow on other paths. We have loops so that if one path opens, even if there's no other parallel path, it can flow around the loop. So with loops and multiple paths, when you lose a transmission line, the original flow will redistribute on all the other lines of the system. And we'll say that the idea is that P sub L after that outage equals P sub L before the outage plus LODF, it's a fractional number, times P sub K, 0. And this one has to have L and K, meaning outage of K distributed onto L. That's the fraction of the line K that gets on there, and you add that to the original P sub L to get the new flow. And the whole point of contingency or security analysis is that if this outage adds so much power to this one that this one is now overloaded, you need to work on the system. You need to adjust the flows through generation changes or through your interchange contracts so that you don't overload it. That's that simple. And what we'd like to do is to do this very rapidly. So if we've calculated this ahead of time, and we know these flows, let's say we measure them, when we bring the measurement values to the computer, they're stored there, then it's a multiply and an add, and then you can compare it to a limit. So you don't have to solve a power flow. You don't even have to solve the linear power flow. So that's an advantage. So you do this for rapid contingency analysis. Now, we're going to use the linear power flow. I'm going to go back over that for you. You know, the representation of a transmission line in per unit system in an AC system looks like this. Now the capacitance is literally the capacitance between the wire and the ground. This represents the resistance in the wire itself, and this represents the inductance. Even though you don't see a lot of turns, there's inductance, there's series inductance. So there's an Rij, an Xij, and then this has got a capacitance. See, I just like to say J B cap Ij, J B cap Ij. This is I, and that's J. Now, if we say Vi and Vj are identically 1 per unit, and we say theta I and theta j are small, and you can find papers that'll discuss this, how small and what kind of errors to expect. In any event, we can then come up and say Pij is 1 over Xij theta I minus theta j, where these are in radians. Both of these are radians. This is the per unit, and this is per unit megawatt only. Okay, now you know that in reality we have a voltage magnitude VI and a theta I, and we have VJ and theta J, and we have PIJ, and we have another arrow that's got a little cross member like this, that's QIJ, the reactive power. We are ignoring the voltages, magnitudes. We are ignoring the reactive power. We are ignoring the resistance. We are ignoring the capacitance. But this approximation is about plus minus 5%. That's a number that we kind of, it's more of a belief than anything. No, but it's a reasonable assumption. If the voltages are way different than 1, the phase angles are not small, etc., then this thing can have a much bigger, a much worse error. Okay, so let's take our little 3-bus system here, and we've got 1, 2, 3. Now, for the sake of analysis, you can draw I call it the injection, P1, P2, P3. It's always the net power into the bus. If the bus has a generator and a load, then we just simply say, and this is bus, let's say this is bus I, then this is PI, and PI will equal, this is P-gen, P-load, is P-gen minus P-load. Because the power from the generator goes in, whereas the power to the load comes this way, comes out, and we're just saying the PI is the power into the bus, which is then the power that goes out, summed over all of those lines is equal to PI. Okay, so P1 is P12 plus P13. So here's P12 and P13, and that's equal to 1 over x12 theta 1 minus theta 2 plus 1 over x13 theta 1 minus theta 3. That's the individual. Here's the x12, x13, x23. Now I'm going to gather the terms. It's always better to gather the terms up so we end up with a linear equation that's can be put in a matrix. 1 over x12 plus 1 over x13 theta 1 minus 1 over x12 theta 2 minus 1 over x13 theta 3. And I'm going to do this with all 3 buses. And I'm going to end up with something times theta 1, something times theta 2, something times theta 3. Okay? And so the P2 equation, this is P1 here. P2 equals minus 1 over x12 theta 1 plus 1 over x12 plus 1 over x23 theta 2 minus 1 over x23 theta 3. Now notice again, theta 1, theta 2, theta 3. If it's the equation for bus 2, then this summation occurs at the theta 2 term. The other terms have negatives. Those are some rules that you can use to check your work or to actually to build the matrix if you want to. So then this one becomes minus 1 over x13 theta 1 minus 1 over x23 theta 2 plus 1 over x13 plus 1 over x23 theta 3. So there's the three equations of the linear network. And what we want to do now is form them into a matrix like this: 1 over x1 plus 1 over x2, and that's minus 1 over x1 minus 1 over the 1, 2, 1, 3. This is 1, 2, 1, 1, 3. Minus 1 over x1, 2. Plus 1 over x1, 2 plus 1 over x1, 3. All I'm doing is just picking off all the terms. 1, 3 minus 1 over x1, 2. 1 over x1, 3 plus 1 over x2, 3. Theta 1, theta 2, theta 3. I made that three equations into a matrix that I call B sub x. Excuse me, B sub x. And so I can say a vector P is equal to B sub x times a vector theta. And that's that equation, like that. The B sub x matrix is n by n, where n equals the number of buses. Okay? Now, we need to talk about the reference bus. If you're talking about a phase angle is always referenced to something. You can't reference it to ground. You can't reference it to 0 volts like you can with magnitude and say, well, ground represents 0 volts. But what represents 0 degrees? Okay, what represents 0 degrees? And in the power system, it represents the phase angle difference between buses, or the difference between a specific bus and the reference bus. So we always say theta for the reference is equal to 0. So one of these buses has got to be a reference bus. And what I'm going to do, let's say here that for our little system like this, 1, 2, 3, I'm going to make this the reference bus. And if I do that, then what I have to do is take Bx, and I will often, you will see, I stick the word alt next to it in various programs and stuff, meaning I've altered the matrix so that the third row and column are zeroed out except for the diagonal, which has a 1 in it. If you go back to this matrix up here and you try to invert it, you will get an error. If I took the first 2 rows and just simply added them together, if I took the first 2 rows, am I correct on that? This should be 2, 3, yeah. If I took the first 2 rows and added them together, I'd get the third row. So that's the definition of a singular matrix. If there's a linear dependency between rows, you can't invert the matrix. Okay? So, therefore, I have to do something. And the something is to declare theta 3 equals 0. Now, I'm going to give you this speech over again several times. I could simply eliminate the third bus out of the equation. I could come up here and say, well, just forget the third bus and the P3, forget the theta 3, and I have a 2x2 system of equations. That might look easy because here I picked the last bus. If you have a large network and you have a reference bus that's not number 1 or number n, but something in the middle, then you form the B sub x, and then you pull the rows and columns out of it and kind of push it back together again. You can do that with computer programs. You can do that. But I guarantee you will spend half your life debugging the program because you're compressing the rows and columns and trying to, and then you have to remember, now let's see, the reference bus is number 100, but we eliminated it, so what is now 100 is really 101. You go crazy. And much of the gray hair on my head is because I used to do that kind of thing. I used to try to, reorder things to get rid of the reference bus and so forth, and it's not necessary. You're better off to do this. It's a perfect placeholder, and it makes the matrix non-singular. You can invert it, and it holds the place, and it solves for the reference bus. So all we have to do now, this of course is 1 over x12 plus 1 over x13 minus 1 over x12, 1 over x12 plus 1 over x23. Whoop, this is x. 1 over x23. And these are zeros, and that's a 1. And now when I do this, I have a matrix. B alt can be inverted, so now I can write theta 1, theta 2, theta 3 is equal to bx alt inverse times P1, P2, P3. Now, I know that this is 0. Theoretically, I don't know what this value is. So, and if I put when you invert this, you still get the zeros and ones. So then I should say, does this equal 0? And the answer is not necessarily. The idea is that you're not going to try to solve for the reference bus power with this equation. You're not going to put anything, no matter what you put in there. We're going to force theta 3 equal to 0. So I don't really care what I put in here, but you have to put the P1 and the P2 value, and you'll get theta 1 and you'll get theta 2. And it turns out that P3 is always equal to minus P1 minus P2. It's the negative of the because they always add up to 0. There are no losses in this linear network. And it doesn't. That's a minor put, but by putting P1 and 2, I can solve for theta 1 and theta 2. If I have theta 1 and theta 2, and I know theta 3 is 0, I can solve for the power flowing. I can draw the flows out here, and I can solve for each flow and get the reference bus flow. Okay? Minor point, but now, there's some other things we need to note here. Let's see, this is page 4. Linear power flow. No losses. So, if you are doing a problem where you have to take into account losses, then you probably want an AC power flow. There were a number of papers written in the 1950s, 1960s that showed approximate loss models based on the linear power flow. Those have gone completely out of favor as far as I'm concerned. So there are no losses. All voltages equal 1.0, which we know is wrong. Okay, the flows are accurate to plus and minus 5%, maybe plus and minus 10%, definitely. But that's not very good if you're really looking for a precise flow. You need an AC power flow. So that's kind of the bad news. The good news is that the linear power flow is very fast. And I can do all this nice sensitivity analysis that I can't with AC. Okay, I can't do things with the AC. All right, so let's look at our PTDF factor here. So here we go. Here's the S, the send bus, and I'm going to put delta P in here, and here's the receive bus into the load, and I'm going to get delta P into the receive bus. Here's the R. And here's my line over here that goes from I to J. And this will be line L. So I want to know what is the PTDF for line L from S to R. Let's see. I'm sorry, I'm going to do it I'm going to do this differently. S to R onto line L. We're going to order it that way. So the equation is that the change in flow on line L is equal to PTDF SRL times the delta P, which is going from S to R. And that the flow L new is flow L original plus PTDF SRL delta P, S to R. Now, under what circumstance would you use these factors? And it turns out there's a lot of uses for them, but one of the things that our present open access deregulated or markets, what are often called deregulated power system. It was originally that the utility had a license to sell power in a certain area, let's say a state, and all the loads in the state had to buy from that electric company. No choice. The electric company owned the generators, the transmission lines, the distribution system, right up to the transformer at your house, and you had to buy from them or you just didn't get electricity. You could disconnect. You didn't have to buy, but that's the only one you could get it from, unless you want to generate yourself, which would be too expensive. Well, now I can have multiple generators, and this is generator company A, generator company B, etc. We'll draw a third one, Genco C, and over here is a customer. And the customer wants to buy some power. Well, before the transmission operator or the ISO goes through and sets up everything, the customer gets a phone call from each of these guys. Okay, they communicate and they bid. They say, listen, we'll sell you. Well, the customer has posted someplace, I want to buy I want to buy, now let's make it easy. I want to buy 100 megawatts from 2 to 3 p.m. on Friday. And they each bid, and they give him different prices. And so the customer picks the lowest price. Now that's the first step. The problem is, so let's say that B was the lowest price. So now he's going to be the S bus, the send. And he is the receive, or the R bus. So he's got a supplier who has an extra 100 megawatts that they can sell from their generator at 2 to 3 p.m. on Friday. The question is, can this 100 megawatts get through the transmission system to the receiver? Can it get through there? Now this is called a bilateral transaction, for the obvious reason that you've got a buyer, and a seller, and a buyer. You get two companies, two people. Let's say they're companies. The customer over here is, if he's going to buy 100 megawatts, let's say it's a big industrial plant. Now, the question being, can I get the power through? If you're really close, that may not be a problem. But suppose he's a customer in Ohio, and the generator is a generating company in Minnesota. If you just think about a map of the U.S. for a while, that power has to go through transmission lines that are going to bend around the bottom of Lake Michigan and go over to Ohio. Some of them are going to go through Minnesota to Iowa, and then go from Iowa through Illinois and back up into Ohio. But there's many, many, many paths. And the problem is, can the 100 megawatts be sent from from S to R? Here's the S bus over here. From S to R without overloading anything. Well, the first thing that has to happen is that somebody has to have a big database that says, well, how much load is going to be on the system, and they have to estimate that, and they do that by by looking at all of the bilateral transactions that are out there and adding them all up. And there's a lot of, if you're the first one, if you're not the first one, well then you don't get, so there's issues of who gets in there first and who doesn't. But the whole point is, if I've got this line out here, and I know this is line L, and there's an initial flow, I'll just write F sub L 0 from N to M. How much is this 100 megawatts going to add to this line? Well, if I've calculated the PTDF, then I just simply say flow, I'm going to just use FL new equals FL original plus PTDF, and this is, let me get my notation right here. So it's S to R for line L times delta P, which in this case delta P equals 100 megawatts. And this is a fraction. It's a fraction. It can go negative, and the only reason it can go negative is you see NM. Well, if I describe this line as being from M to N, then the flow in this direction will be considered a negative flow. That's a minor point, but you should know this PTDF can go between plus and minus 1. So it's a fractional number. So PTDF is from minus 1 to plus 1. Okay? Minus 1 to plus 1. So now, what I'm going to do is I'm going to say, well, how do I calculate that? And actually, it's very simple. I'm going to take the inverse of my B sub x matrix. Now, let's assume that we've done the zero out. And I'm going to take B sub x, I'm going to alter it by zeroing a row and column out in inverse, and I'm going to call that, because this had 1 over x's in it, now this one will have x's, so we call that x, cap x matrix, okay? Instead of, this is B sub x becomes all by taking the zeros, zeroing row and column out. So, then theta 1, theta 2, all the way down to theta n equals x times P1, P2, Pn. Now, what I really want to know is something about delta P. And it turns out that if it's a linear system, I can write this equation with deltas, and I get the same equation. And I can write delta theta 1, delta theta 2, delta theta n. It's still the same matrix. Delta P1, delta P2, delta Pn. But now I'm going to say, well, look, here's, if this is S up here and this is R down here, then I'm going to say that all of these equal 0. They don't do anything, except S, delta S, he's the sending bus, becomes a plus 1, and delta PS, and delta PR becomes minus 1. So this is a plus 1, this is a minus 1, everything else is 0. So all I'm doing is I'm going up to the power system. I'll draw it down here again. Here's my seller, here's the S bus, plus 1 in here, here's the receiving bus, and I'm taking a plus 1 out here that's going out, so it's a negative 1, right? So this is delta PS equals plus 1, delta P at the receiving bus is minus 1. Nothing else does anything. There's no injections, there's no changes anywhere. And I will be able to now calculate the change in phase angle. We can see that on the next page here. Delta theta I equals XIS minus XIR. Delta theta J equals XJS minus XJR. Therefore, the change in flow on line L, and we'll just assume that line L goes I to J, is 1 over X Ij delta theta I minus delta theta J. So this is then 1 over Xij up here, capital X. I should put these big lines so that you know that these are terms from the X matrix. These numbers here came from that matrix. Okay, they came from that matrix. So it's XIS minus XIR plus 1 over X Ij. Oh, I'm sorry. This term, I don't need that. I've got that bracket. XJS minus XJR. And we'll put a big square bracket around it here, with the 1 over Xij for the line itself, and then I have to get 4 terms out of that X matrix, and that delta FL, and that is the PTDF from S to R for line L. And it's that simple. Now, people, this is an example where you do not want to calculate the entire inverse. You do not want to calculate the entire inverse. In fact, this is row I, column S, row I, column R. So I can get both of those terms from row I can get both of these terms from row J. And it's very easy to calculate just the row of an inverse matrix. And in this case I need 2 rows of the inverse matrix. And I don't need all the other terms. I do need each row. I need 2 rows for each of these PTDFs. So I'm not going to get into that. We had a separate course on sparse matrix techniques and so forth, but I'm not going to go into that right now. But PTDF, you don't want the entire X matrix. Although if I'm doing a little MATLAB program, I probably would just generate the inverse itself. There's a couple of rules that I want to come in here and make sure that we understand issues, so to speak. And they are that, suppose I have this. These lines, I call them radial. So here's line L, here's line K, and this goes from I to J and from N to M. Suppose this is S and this is R. Well, in the first place, the PTDF, because it's a radial line, every line in there will have a PTDF. The PTDF S to R to L equals +1 because all the power goes through there. And the PTDF here, PTDF from S to R for K is equal to 0. None of the power that goes from here to here, if there's a generator here and a load here, none of that power will flow through this radial line. Therefore, it's 0. And in the book, we go through and make sure that we issue some warnings about that. The codes that I have for those things, you have to recognize that specifically, and you have to be able to find the radial lines. Otherwise, you might get some divide by zeros. All right, next is my LODF. The LODF is technically, it's the change in the flow on line L when divided by the flow K original. So this is the flow that's dropped. FK is flow on K before it opens. Before it opens. Okay. Now, and so therefore the FL new is FL original plus LODF, L to K times FK original. Very simple. Very simple. And what we do there is we build, to do this, the logic is in the appendix of the chapter. I'm not going to go into it too deeply here, but the idea is if I have a bunch of lines like this, and I have a line that I want to take out, and here's other lines over here. So this is line K right here. I'm going to take that line out. And what I do is I say, well, look, let's suppose then that those 3 lines on the outside, they come down, and there's there's a breaker, and there's line K, and it goes back up in here. Here's all the other lines. That didn't change very much. But now what I'd like to do is I'd like to say, well, I'm gonna put some injections. I'm gonna say that there's a flow through this line originally. Only what I want to do is simulate when the line is opened. But I'm not going to take the line out. I'm going to put a thing in here called delta P, and I'm going to take delta P out here, and that delta P is going to flow right through the line and back out. So it's going to flow like this, okay? And I'm going to adjust the value of delta P. Some of this power will flow out into the network and back in over here. What I want to do is make sure that what's flowing through these breakers is 0. So I'm going to run this up and down, and this will go up and down in the same proportion, except this one is coming out and this one is going in. As I said, some of the power goes around and comes back in the other way. That's okay. Once I get the power in here, the P in the breaker equal to 0. Same thing over here. Then it's got 0 power flowing through the breakers. It doesn't matter if the breaker opens or not. I said I was going to leave the line in, but if there's no power flowing through it, then these powers here can be used to calculate what happens to everything else on the system when you open this line. And you can see the logic it gets into pages and not pages, but a couple of pages of algebra. But it's in the textbook. Now, one thing that there's a couple things I wanted to warn you. PTDF, LODF must be recalculated if the network changes. So if you open up a line, then all the PTDFs and all the LODFs are going to change. That's strictly not true. Some of them may not change, but you might as well figure that they're all going to change. If you open a line, if you split a bus, if you have a bus with a breaker like this, and you have 2 lines coming in here and a third one, and maybe this one just has one going in and one going out. This is normally one bus, and then I open that breaker, so I now have 2. I now have 2 buses. Then you have to recalculate all of the PTDF and LODF values. That's a distinct disadvantage. I like to tell the story that in here's New York State. Here's Long Island going up like this. Here's New York. I used to live there, so my maps of New York are probably much more accurate than they are in Minnesota. And up in right in this region, there was a substation. And one Sunday, a great big electrical storm. Boom. Boom. Lightning striking. Okay. And the storm came over the substation and struck one of the lines, and a line opened. So up in Albany, New York area was what was called the New York Power Pool. which controlled all the power flow in New York. It was built to study security and so forth. Well, it found out that there had been a line opening, and so on a timeline like this is here you've got the strike, and they started a process of rebuild PTDFs, LODFs. They wanted to do contingency analysis after this line went out, so they started rebuilding them. And the problem is, they're right in the middle of the rebuild. They got another strike here. They got another strike. So I'm doing that with the purple. And so right here, you got to stop. Everything you did is no good, and you might as well discontinue and start recalculating again. And I think that they did that a couple times. They had the computer systems simply got halfway or got part of the way through again. So you had a long period of time while they're recalculating the factors, and then there was a third strike over here, and the net result was that there was a lot of power coming across New York State from the Niagara Falls generators, down from Canada, from the Messina plants, into New York City. This substation completely opened up. They cut it off, and New York City had a blackout. And it was one of the worst that we've had in the United States from the following viewpoint. It was a hot, humid Sunday afternoon, and the power went out. People went out on the streets. Their air conditioning was off, and there was rioting. There was looting. It was a terrible thing. One of the first blackouts, I think, and maybe one of the last, where there was widespread looting of stores and so forth. The police couldn't keep up with it. And that was because they had to recalculate these factors. Today you have much better computers, much faster computers, and better techniques than to calculate all these factors every single time. So be that as it may, we don't do that anymore. But that's one of the disadvantages. Now, another thing is, suppose I'm back to this bilateral transaction business again, and here's my generator S, and here's my customer over here, the receiving point R, and I've got line L. I can calculate the PTDF, okay, for this line. And I've also got a line K over here. So let's say if I put the transaction on, then FL new equals FL old plus PTDF. Now again, it's S to R for L times F times, this is the delta P, S to R. Remember, this is delta P, and delta P is coming out here. And FK new equals FK old plus PTDF, only this is S to R to K, and it's the same delta P, S to R. I can tell you how much of this gets on this line and how much this one changes. And now suppose I say, well, what if during the transaction I also have an outage? So the nice thing, you know that a linear system allows you to do, you may not have thought of it this way, but when you had circuit analysis, assuming you're an electrical, well, even if you're a mechanical engineer, you've had some circuit analysis. we can use superposition. So I can say the effect of the transaction from S to R, that's one thing, and on line L, added to the effect of a line outage on line K. And so what I need to know is, it's FL. So this is new with outage is equal to FL new plus LODF FK new. Well, this is equal to, this one is FL0 plus PTDF times delta P, and this is S to RL plus LODF, and this one is FK plus PTDF S to RK delta P. So there's, all I did was take the flow values that were determined by the PTDFs. We did that on the previous page. Given the PTDF tells me the transaction, how it affects line L and how it affects line K. And then I can just insert those values into the LODF. And if you do this, you can say, look, FL with new flow with outage is going to equal I'll put it in here, F0 plus LODF times FK0 plus, and it's equal to PTDF plus LODF times PTDF. Well, this is what? SRL. This is LKSRK. And then that's times delta P. This factor now tells me, given the transaction amount, how much do I expect that to change the flow on L. And so they sometimes call this an OTDF, or outage transfer distribution factor. OTDF, you'll hear it referred to as that. Now, why would you want to do that? Well, again, if I'm doing a bilateral transaction, and actually this is the rule, the way they do it, they tell you you cannot add it on if any first contingency flow with the transaction will result in an overload. Any first contingency, that's the line K out, will then result in an overload when you have added your transaction. So that's one of the problems that you have. There's one other kind of factor that I'm gonna talk about, because it's gonna come up later on in the course, so I might as well get it out here. And that's called the A factor. How did it get the letter A? I don't know. I used it in the book, the very first edition of the book, but I think I got it out of a technical paper. But here we've got we want to develop something called the flow matrix. I'm sorry, I don't need to talk about the flow matrix. I'll come back to that next. But let's just take, and we're going to say here's our transaction from S to R. Delta P going in, delta P, and delta P coming out over here. And what I'd like to know is, suppose I don't do it this way. Suppose I do it this way. Delta P, power going in, and over here is the reference bus. And so if this is delta P, then this one, delta P, the reference bus responds in the opposite direction. And therefore, all I've done is I've increased the power out here and the reference decreased. Okay, and then line L, I to J. And it turns out that the A factor is FL new equals FL old times A L S. This is S. Is all the reference bus. I don't have to. That's just the reference bus times delta P. Okay. Now, in the formulation that we had for the PTDF. Remember, we had X, capital X's. We had 4 of them. Here you're only going to get 2. You're going to get 2 terms because you have delta. Delta theta 1, delta theta 2, and so forth, and you have your capital X's, X11, X12, etc. And then over here, remember that someplace in here, I've got zeros for my reference bus. So this is the reference bus, and so here's the P ref. Well, I don't need to worry about it. So I'm just going to take at the S here, I'm going to put a +1. And this one I don't care. In fact, I should probably just put a 0 there. Well, then the changes delta X, delta theta I is X I S, okay, times this 1 over here, and delta, this is I, delta theta J is X J S. So then the A factor is simply 1 over Xij, Xis minus Xjs. That's it. It doesn't need. It only needs 2 of these cap X terms here. I didn't put the top and bottom on them. There it is. So that's the A. So A simply is the same thing as we had from going in here and out here, but it's in here and out the reference, and then I don't need, and it's a simplified version of the PTDF. The other thing that's going to come up, and we will see it in the homework that's going to be issued in a week or so here, is something called the flow matrix. Well, if the flow Pij equals 1 over Xij theta I minus theta j, then here's the flow. Here's Pij and Pnm and P. Let's see, A, B, etc. Here's all the flows. So here's 1 to number of lines. And we've got a matrix over here. And theta 1, theta 2. This isn't as long. I should have drawn it shorter here. So this goes from 1 to n, where n equals the number of buses. And then wherever I have a row and column, I'll have 1 over xij minus 1 over xij for the in the column I and the column j. This one will have 1 over xnm and minus 1 over xnm, and in columns n and m. And then let's say a and b are out here. A and b will have 1 over xab and minus 1 over xab. And therefore, when I multiply this, everything else in here is 0 except those terms, and each row has only 2 terms. Has 2 terms. All else equals 0, and so it's n lines by n buses, if you will. And that's the flow matrix. You multiply it by the phase angles, and you get the flows. Now that turns out to be a very useful matrix. Later on, we'll be using that in some of our other calculations. Okay, so that's the short form of the lecture that you received on February 28th. At the EE department there, and I will now post a copy of these notes and a copy of the video. Bye-bye.